Chapter 10 is about what we call hypothesis testing. Okay. This video at first may seem a little strange. I'm just going to be introducing you to some vocabulary and some symbols that we're going to use, and then in the next videos we'll start working some problems, and I think it will make a little more sense, but just bear with me. Try to get comfortable with the vocabulary and some of the notation, kind of procedural things, and then I think it will make more sense when we start working some problems in 10.2. Okay? All right, a hypothesis. You probably have heard that word before in science class. A hypothesis is a claim or a statement about a characteristic from our population. Okay? A hypothesis test is a procedure or a process based on evidence and based on probability that we use to test a claim. Okay? I knew a professor one time that said a hypothesis test was a decision-making process. Okay, so you're going to make some decision, whether it's deciding what to eat for dinner, deciding what shirt to wear, whatever the case may be, you have to make a decision. And a hypothesis test is a way to make that decision. Now, obviously, in a stats class, the decision that you're going to be making is probably not what to eat for dinner or what shirt to wear. It's going to be, are we going to believe that the mean really is whatever number for the scenario? Or are we going to believe that this proportion of people do whatever the activity is? So that's the decision that we're trying to make, whether we believe that or not, okay? Whatever our hypothesis is. Now, keep in mind, we are using sample data. So in other words, if I needed to decide whether this new treatment was going to really work for the coronavirus, I can't test every single person in the world with this new medication and see if it helps them. I can only test a small group, a sample. So we cannot be 100% certain that this new medicine really is going to be, the cure. We can just test it on a few people, and if it seems to be working on them, then we can say, yeah, we think it works. Give it to everybody. But we can't be 100% certain, okay? That's why it's a hypothesis. We think it's going to work, and we test it to say, yeah, pretty sure it's going to work, or no, we don't think it's going to work. But you really can't be 100% certain, okay? We just try to decide if there is evidence there to support the claim that the data is that the new medication is going to work based on our data, okay? All right, first part of any hypothesis test is to state our hypotheses. And there are two. There is the null hypothesis and there is an alternative hypothesis. Okay? The null hypothesis, we use the symbol HO. Okay? The alternative hypothesis, we use the symbol either H1 or HA. Okay? Personally, I like to use HA for the alternative because then I can say I have a ho and a ha. Okay, the ho is the null hypothesis, the ha is the alternative hypothesis. Some books, though, instead of HA, use H1. Our book is one of those that does that. So they use HO for the null and H1 for the alternative. Okay. Then you're going to have a symbol in your null and alternative hypothesis. Your symbol will be either mu, if you're dealing with means or averages, or it will be P if you're dealing with proportions. Those are the only two symbols that we will use in our course. Mu if you're dealing with means, P if you're dealing with proportions. Okay? Your null hypothesis will always be mu equals some number if you're dealing with means, or P equals some decimal number if you're dealing with proportions. Okay? Now, in a hypothesis test, you assume that the null hypothesis is true. We assume that null is true until evidence indicates otherwise. Okay? If you get evidence saying, we no longer believe that null hypothesis is true, then that means you're going to reject the null. You're going to go, no, do not believe you, I'm rejecting you. Okay? If there is not evidence that you reject the null, then you do not reject it. Notice I did not say that you accept the null, or that you believe the null, or that you support the null. Okay? You either reject it or you don't. Okay? There was not evidence to reject it, so we don't reject it. That doesn't necessarily mean it's true. We just don't reject it. Okay? That's a very subtle difference in the language, but it is kind of important. Okay? And if you think about it, you have some experience or some indication of that phrasing before. For example, in a court case, the jury listens to all the evidence. Here's all the testimony about the evidence in the court case, and they either come back and they say guilty or they say not guilty. Okay? They either say, you know what, based on the evidence, we believe this person is guilty, they did it, or we say, oh, this person is not guilty. If they say not guilty, that doesn't necessarily mean innocent. That doesn't mean the person didn't do it. It's just they didn't have the evidence to say guilty. And it's kind of the same thing here with our null hypothesis. We either reject it or we don't reject it. Okay, and there's a subtle difference in that language there. Okay, all right, the alternative hypothesis. The alternative hypothesis will be one of three different scenarios. Remember, the null always has equal. Always, always, always has an equal. The alternative hypothesis will have one of three symbols. It will either have a not equal to, meaning, if the null that said the mean was equal to some number, then the alternative could be, the mean is not equal to whatever number that was. Okay? Or if it was a proportion, you would say proportion is not equal to whatever that decimal was. Or your alternative could say, hey, I think it's a particular side. I think it's greater than. Maybe they said the mean salary was, $10 an hour, and I think the mean salary is more than that. So the mean is more than $10 an hour. Or if your null hypothesis had been, I think 35% of people like chocolate chip cookies, and you go, no, I think it's higher than that. Then you would say, okay, I think the proportion is higher than 0.35. Okay? Or the third way you could set up your alternative hypothesis is with a less than symbol. So if you think, I think the average age of people when they get married is less than 20. So then your null might have said mean equals 20, and your alternative is mean is less than 20, or whatever age it was that you were working with. If the proportion of people who believe in love at first sight, maybe it's 60%, and you think, no, I think it's less than 60%. Then your alternative might be P is less than 0.6. Okay? So your alternative will either have the not equal to symbol, the greater than symbol, or the less than symbol. Has to be one of those three scenarios. The equal to always goes with the null. Okay. Once you decide your alternative hypothesis, whether it's a not equal to, a greater than, or a less than, that is going to determine which type of test you're going to do. A two-tailed test means that you picked the not equal to symbol for your alternative hypothesis. Okay? Two-tailed test means that you said not equal to in your alternative hypothesis. Okay, so let's say that this was a proportions problem. Maybe we said, 50% of the people in America are fans of the Dallas Cowboys. Okay, so we think the null would be 0.5, and then you said, no, I don't think it's 0.5. I don't know if it's higher, I don't know if it's lower, but I think it's not 0.5. Okay, well, then you would be saying that you would be saying then that your percentage of people is not 0.5, could be below or it could be above, but it's not equal to 0.5. So in a normal distribution, you think it's one of these two ends out here. So it's a two-tailed test. You're not committing to whether it's the low end or the high end, but you think it's not 50%, not the part that's in the middle. Okay? So you would be doing a two-tailed test. Okay? That happens when you have the not equal to symbol in your alternative. A left-tailed test occurs when you picked a less than symbol, less than left-tailed. Okay? So left-tailed test occurs when you say, nope, I think it's definitely on the low end. On my bell-shaped distribution, I definitely think the proportion is below the 0.5. That's a left-tailed test. Okay. Right-tailed test would be when you have a greater than symbol. You said, nope, I think it's more than 50% of the people are Cowboys fans. So I'm betting it's above the 0.5. I think it's higher than that. And you're picking a right-tailed test. Okay? Now, notice they keep referencing in this definitions here, they represent this little symbol right here, the alpha symbol. We will talk more about what that alpha symbol means later, but it will be given to you in your problem, okay? In a lot of scientific studies, a lot of hypothesis tests, when scientists actually do them, they often pick 0.05 as their alpha, and that is called the level of significance. And we will talk more about it later, but just know that that alpha number will be provided for you. Okay, most of the time in scientific processes, it's 0.05, but it could be another number besides that. Okay, so we are going to practice writing some null and alternative hypotheses and deciding whether we're dealing with left-tailed, right-tailed, or two-tailed test. Okay. The percentage of male voters is less than 4%. Now that is a claim. That is what someone believes. That is someone's hypothesis that they are trying to collect evidence to support. Okay? All right. So they are talking about percentages. That's proportions. That means our symbol for our null and our alternative hypothesis has to be a P. Okay? The null always has the equal. The alternative will either be a greater than, a less than, or a not equal to. We'll have to make that decision. The number they give us is, they said 40%. Now we can't put percentages in our problems. We have to use decimals. The decimal of 40% would be 0.4. So my null hypothesis is that P equals 0.4. Our null hypothesis, what we assume to be true, is that the percentage of male voters is 40%, but we are claiming, and our claim is always the alternative, we are claiming, we believe, according to this statement right here, that it's actually less than 40%. So our claim, our H1, is that P is less than 0.4. Okay? Because we picked a less than symbol, we are putting the tail on the left side. Less than left side. We are putting the tail on the left-hand side. Okay? So this is a left-tailed test. We'll talk more about what that means later. Just know for right now that it's left-tailed. Okay, another example. The mean amount of water in a bathtub is more than 124 gallons. Now they said the mean. Okay? Because they said mean, we know we're using mu as our symbol for our null and alternative hypothesis. Okay? They mentioned the number 124 for 124 gallons. I have no idea how much water a bathtub holds. That seems reasonable to me. 124 gallons seems like a lot, but okay, that's what they think a bathtub may hold more than that. Okay, remember the null always has the equal, and the number they've given us is 124. So our null hypothesis is that the mean equals 124. The average bathtub holds 124 gallons of water. Our claim, what someone believes, and they are designing this experiment around and they're trying to prove, okay, is that, or they're trying to gather enough evidence to support, I should say it that way rather than prove, they're trying to gather enough evidence to support that the average bathtub will hold more than 124 gallons. So that is our claim. That is our alternative hypothesis. Because it says greater than, that means our tail will be on the right side. The tail is on the high end. The tail is a large number. So this is a right-tailed test. Okay? All right. As we work through this set of notes, we're just going to be kind of talking about vocabulary. These are kind of the steps that we're going to follow when we solve some problems later. So just kind of, bear with me on the Roman numerals there. Okay, next step after we write our null and alternative hypothesis and decide if we're doing left-tailed, right-tailed, or two-tailed, will be to determine the alpha level. Remember, alpha stands for level of significance. That number will be provided for you. If you were a scientist doing your own experiment, you would get to choose that number yourself. Most scientists pick 0.05. Okay. But level of significance or significance level, those are the words that mean that alpha symbol. Okay? Based on your alpha level, you will determine a critical value. The critical value will come from a table that is in your formula chart. Okay? You will use either the Z table or the T table. Okay? On your formula chart that we have here, on the very last page, there are two tables. The one at the top is the Z table for a Z distribution. The one at the bottom is the T table, the T distribution. Okay? We use the Z table up here when we're dealing with proportions. So if your null and alternative hypothesis had P's in them because you were doing proportions, you would use the table at the top. If your null and alternative hypothesis had means in them, had mu's, then you would pick the T distribution, which is the table at the bottom. Okay? I think the best way to remember that is to think about mean Mr. T. If you've ever seen, the A-Team, or if you know who Mr. T is, he says, I pity the fool and all that. Okay? I always think mean Mr. T. He seems like a mean guy. So if you're doing a problem with means, you're going to use the T distribution. That's the table that you're going to use. Okay? All right. I'll show you how to use that table in a little bit. Okay? All right. But you are going to use that table, either the Z or the T, to get your critical value. Okay? Just so you know, that level of significance is the probability of making a type 1 error. There are two types of errors, type 1 and type 2. Okay? Type 1 is going to be the probability of a type 1 error. That's going to be your alpha number. Okay? We'll talk more about what that means later. The critical value is going to separate, okay, the critical region from the values in your test statistic that do not lead to a rejection of the null hypothesis. Okay? Sometimes instead of a critical region, sometimes I like to call it a rejection region, just that, RR together helps me remember a little bit better. Okay? If I have a two-tailed test, remember I've got my low probability or high probability, those two tails. Okay? Alpha is split up between these two. Okay, so if my alternative hypothesis maybe said P did not equal 0.5. Okay, I do not think that half the people or 50% of the people are Cowboys fans. I don't know if that 50% is too low or too high, but I don't think it's 50%. So I would be doing a two-tailed test. Okay, that alpha, if my alpha was 0.05, that 0.05 would be split between these two regions. So 0.05 divided by 2 would be 0.025. And 0.025. Notice that the 0.025 and the 0.025 would add up to 0.05, which is our 5% that we commonly use for our alpha. That means 0.95, 95% of the time, 95% of our data, it should be in between. Okay? So that's where that's coming from. All right, left tail test. All of alpha would go in the left tail. So instead of having two tails, I just have one on the left, and my entire 0.05 is on this left end. My 0.95 is not only the middle, but the middle all the way to the right edge. Right tail test means your entire tail is on the right side. Your 0.05 is on the right, and the entire 0.95 would be on the left. So whatever alpha number they give you in the prompt, that alpha is in the tail, whether that tail is on the left or the right, or it's split in half for the two-tailed test. Okay? You will get a critical value. That critical value will come from a table, and that will be a cutoff number right here. Okay, so let's say my critical value was, I'm just going to kind of pull these, I'll show you how to use this table in a second. If it's right-tailed at 0.05, your critical value would be 1.645. So 1.645 would be my critical value. And then the test statistic that I get from my calculator in a minute, what I'm trying to do is see if that test statistic falls in this rejection region or not. And if my test statistic in my calculator is in the rejection region, then I will reject the null hypothesis. If my test statistic from my calculator is not in the rejection region, it's down here with this other 95%, then I will not reject my null hypothesis. Okay, and we'll look at examples in a minute. I know that that language is kind of strange. Notice this table right here is a match, pretty much. There's I think it's got an extra number or two in here in your notes that aren't on the full table. But this is on your formula chart, okay? Notice that the alpha number or level of significance is either 0.1, 0.05, or 0.01. Most of the time in science experiments they use 0.05, but it could be other numbers as well, okay? And it gives you, if you have a two-tailed test, notice your number could be positive or negative. If it's a left-tailed test, it's just negative. If it's right-tailed, it's just positive, okay? If it's two-tailed, you have positive and negative because you've got two different tails. The negative on the left, the positive one on the right. You think about it as z-scores, okay? All right, so find the critical values for a hypothesis test about a population proportion. So our two-tailed test, okay, and alpha equals 0.01. All right, so if it's a two-tailed test, that must have meant that my alternative hypothesis had a not equal to symbol. There's a tail on the left, there's a tail on the right. Okay? So at the alpha level 0.01, so alpha 0.01 with two tails, my critical values are negative 0.2575, that would be on the left, and positive 2.575. Okay? So in a minute, from my calculator, I'll get a test statistic. And I need to see if my test statistic is in this middle region or one of the rejection regions. Okay. Now notice, if alpha equals 0.01, okay, that's the chance of making that error, then there's a 99% chance I don't make an error, 0.99. That 0.99 is the area in the middle, if you think about your normal distributions. Okay. 0.99 is the area in the middle. That 0.01 got split between two tails, okay, and we would get 0.005. So the area of the test statistic, or the probability of the test statistic being in this area is 0.005. The area of it, or probability of it being in this area down here is 0.005. Notice that those three probabilities together add up to one whole to represent the whole area under this curve. Okay. All right, so our critical values would be plus or minus 2.575. That's what they wanted us to find. If we had a right-tail test, okay, well, if we have a right-tail test, then the whole area is on the right. Alpha equals 0.05, so that 0.05, the whole thing is over here on the right. That means 0.95 is the whole rest of it. Okay, so I'll look up at 0.05 for alpha for a right-tailed test, and my critical value, it says, is 1.645. So 1.645 is my cutoff number here for my rejection region. So then when I get my test statistic from my calculator, I just want to see if that test statistic is bigger than 1.645, which would put it in the rejection region and make me reject the null hypothesis. Or if my test statistic is smaller than 1.645, that puts me in that 95% right there, and I would fail to reject my null hypothesis. Okay, test statistic will come from your calculator. You do not have to do any calculations by hand for it. Your calculator will tell you what it is. This is the formula that your calculator will be doing. If you're working with proportions, your null and alternative hypothesis had p's in them, this is the formula that your calculator is doing behind the scenes. If your null and alternative hypothesis were about means, you wrote mu's in your null and alternative hypothesis, then this is the formula that your calculator is using. Remember, we do z-scores from a normal distribution when we do proportions, and we're using that student t distribution when we're talking about means, and so that's why it says z or t. Okay, that's why we use the different charts there. Okay, once you have your test statistic and your critical values, you draw a little picture. And I've kind of already been drawing these for you, but you'll be able to actually label where your test statistic is. Is it in the rejection region or not? Okay. All right. Next, when you ask your calculator to give you the test statistic, it'll be either a z or a t number. It will also give you a p-value at the same time. Okay. Some people, mostly non-math people, non-statisticians, prefer to rely just on p-values, and they don't worry about test statistics too much, okay? However, since this is a statistics class, I think we should focus on test statistics. So we're actually going to use the test statistic and the p-value. But a lot of scientists rely on p-value only and not their test statistics. So I don't know that that's great. I think it kind of shows that maybe they don't really understand what's happening. But p-value is another way that you can figure out whether to reject or fail to reject your null hypothesis, okay? A p-value is the probability of getting a value of your test statistic that is at least as extreme as the one that you got from your sample data, okay? In other words, if we assume that the null hypothesis is true, what's the probability that a random sample would give us a test statistic out in whatever region it's in, okay? If you have a small p-value, that means there is a very low probability that you would have gotten data with that particular value. So that means, you know what, we don't really believe this null hypothesis. We're going to reject it, okay? Let me give you an example. One of the problems in our last chapter had chocolate chip cookies. And there was an old ad campaign that the company promised that you would get, say, 1,000 chocolate chips in your bag of cookies. I don't remember the exact number, but let's say it was 1,000, okay? All right, so if you went out there and bought a bag of cookies and you are expecting to get 1,000 chips, well, probably if you got 1,050, you're excited. You're certainly not going to complain about that, but you got a little bit more than what you were expecting. On the other hand, if you got, so I'm going to say here that my mean is 1,000. If you got more than 1,000, you're excited. If your mean was less than 1,000, you're not thrilled, but you understand, oh yeah, well, I got 980. That's not very much less. That's okay. That's to be expected, okay? So what should happen is the mean might be here at 1,000. You know that you might get a little less or you might get a little more, but you're expecting around 1,000. But let's say you bought a bag of cookies that only had 800. Well, 800's way less than 1,000. Now, could you just be unlucky and happen to get the one bag of cookies that had less, way down here at 800? Yeah, you might just be unlucky. That, it's going to happen. Somebody else is going to get 1,200. Okay? But if you bought 2 or 3 bags and they were all down here around 800, you might really question that null hypothesis that the mean is 1,000. You might go, you know what, I think they're full of it. I think that mean is less than 1,000 because there's no way that I'm so unlucky that I just keep getting less than 1,000. And so that p-value says, hey, what's the probability that you really do get down here at only 800 chips in your bag? And if that p-value is really, really low, like maybe 1%, you're going to go, you know what, the probability of me only getting 800 chips was like 1%. That means I don't believe them when they told me that the mean is 1,000. I think it's really less than that, okay? So that's what that p-value tells you. It says, hey, what's the probability that you actually get a sample of data that's way down here or way up here or wherever you put it, okay? If that p is low, you're going to reject that null hypothesis. You're not going to believe them, and you're going to reject the null and support the claim, okay? However, if your p-value is more than alpha, then that's saying, hey, you know what? You were unlucky. You got less than 1,000, but it's not crazy low. It's not extremely low. It was not super unlikely. Maybe there was an 8% chance of you getting a bag that low. Well, that's not lower than our 5% alpha. So, it's unfortunate for you that you didn't get very many chips, but it's not really low. So we are not going to say it's unusual, and we are not going to reject that null hypothesis. Okay? All right. How are we going to make our decision? When to reject or to not reject the null? Okay? And I keep saying null. Some people like to say ho just because that's the symbol for the null, and that's fine if you want to say it that way. Okay. There's 2 approaches in our notes, and then I'll tell you a third one that sometimes gets used. Okay? Classical approach. The classical approach I sometimes call the rejection region. Okay, I prefer to call it the rejection region. Classical approach says, hey, draw your picture, with your tail, and if you're going to have your critical value right here. If your test statistic falls in the rejection region, or the critical region as our book calls it, then you're going to reject the null hypothesis. Your test statistic was in the rejection region, you're going to reject. If your test statistic did not fall in the rejection region, maybe your test statistic was over here, not in the rejection region, then you will not reject the null hypothesis. Okay? That's option 1, method 1. I think this one makes the most sense visually because you can clearly see, oh yeah, look, I'm way out here in the rejection region, or oh, I'm not in the rejection region. Second way that you can make your decision to reject or not reject is called the p-value approach. This is what most scientists use, okay? I don't think it's as obvious what's happening statistically, but this is the way that they usually use it, and people who maybe are not as strong at statistics, but maybe have a heavy science background, but maybe not as much with stats, they know how to make their decision here, even if in the rejection region they may not as much. Okay, if the p-value is less than alpha, you will reject the null hypothesis. Okay, so let's say that your p-value is 0.05. I'm sorry. Let's say that your p-value is 0.03, which that p-value is going to come from your calculator. And let's say that your alpha is 0.05. That p-value is lower than the alpha value, so that means you will reject the null hypothesis. If you reject the null, that means you're supporting the alternative hypothesis. Okay. Now, I had a student one time who liked to say it this way, and I think it's clever. It's kind of a rhyme that sticks in your head. I mean no offense by it. I'm not trying to call anybody names or anything. It's just a little rhyme that helps you remember. Okay. They used to say, if P is low, reject the hoe. All right, so if that helps you, do it. Okay, I don't know if it's very PC, but if that helps you remember, then you can say it that way. Okay, if P is lower than alpha, if P is the low one, reject the null, reject the HO. On the other hand, if P is greater than alpha, so in other words, maybe P was 0.08 and your alpha was 0.05. Well, in that case, P is greater than alpha, you would not reject. You would fail to reject the null hypothesis or the hoe. Okay? So notice both the classical and p-value approach, you should come to the same conclusion. Okay? Because that p-value is the probability of where this critical value lays. Okay? All right, third one that we're going to see maybe a little bit of, but not a whole lot, is confidence intervals. Okay, we calculated confidence intervals in our last chapter. All right, confidence interval, if the number from the null hypothesis is not in the confidence interval, then reject. If the number from the null hypothesis is in the confidence interval, then do not reject. And we'll see an example of that later, but just wanted to plant the seed that that is a third way that you could work with hypothesis test. Okay. Finally, once you make your conclusion, you need to connect it back to the original claim. Remember our original claims a while ago, we said things like, we think the percentage of voters is less than 40%, or we think the mean amount of water in a bathtub is more than 124 gallons. Okay, so whatever your claims were. If you reject the null hypothesis, that means there is evidence to support your claim, whatever your claim was that you originally wrote, your alternative hypothesis. If you do not reject the null hypothesis, okay, then there is not sufficient evidence to conclude that whatever your claim was. Okay, so let's say that our claim was that the proportion of women who smoke is less than 0.35. Okay, now that's the claim. That's our our alternative hypothesis. Okay, so let's rewrite just so we can kind of organize our thoughts. Proportion, so these are going to be P's. Null always has to have the equal. Proportion of women who smoke is less than 0.35. So my null is that the proportion of women who smoke is equal to 0.35. My alternative is that the proportion of women who smoke is less than 0.35. So by seeing this claim, I know this was the null and this was the alternative. Okay. Now, for now, we're skipping the whole, typing stuff in your calculator, drawing the picture and all that. But just so you know, this would have been a left tail test because it's got a less than. You would have used your table to get the critical value. You would have gotten a test statistic and a p-value from your calculator. And apparently after that was done, the decision or conclusion, whatever you want to call it, was made to reject the null. Well, if they rejected, that must have meant that my test statistic was in this rejection region. If they rejected, then that must have meant that my p-value was less than alpha. P was low. Okay, so we rejected the HO. Okay. P is low, the hoe must go. Okay. So if that's the decision that they made, okay, then that means there is sufficient evidence to support the claim that what? What was the claim? Well, the claim was that the proportion of women who smoke is less than 0.35. So I'm going to restate that. Okay? If I rejected the null, that means there was evidence for me to go along with this claim. I rejected the hoe. That means I'm supporting the claim. Okay? So there is sufficient evidence to support the claim that the proportion of women who smoke is less than 0.35. Okay, we are supporting that claim. We had evidence to support it. In other words, the probability, if the proportion of women who smoke really is 0.35, then the chance of us getting a sample way down here was incredibly low. So that means we don't believe that 35% smoke. We think it really is less than that. Okay, another example here. The mean number of peanuts in an 8-ounce jar is not 200. Remember, that's their claim. That's their H1. Okay, well, if that's the H1, that the mean number of peanuts, they're saying mean, so my symbol here is mu. My null always has the equal, and the number they referenced is 200. So the null hypothesis must be that the mean number of peanuts is 200. Our claim is that the mean number of peanuts is not 200. Okay, well, since we have a not equal to, that was a two-tailed test. They don't tell us, we haven't looked yet in our calculator how to get the test statistic and the p-value, but after we did it, their decision, their conclusion was that we should not reject. Okay, well, if we're not rejecting, that must mean that the test statistic was not in the rejection region. That must mean that the p-value was not less than alpha. The p-value was greater. The probability was higher than whatever level of significance they gave us. Okay? So that means there is not sufficient evidence to support the claim that, and then go back and reread your claim. Our claim was that the mean was not 200. Okay, so the number of peanuts is not equal to 200. Okay, so we did not reject the null hypothesis. Now, that's not a guarantee that the mean number is 200. We just didn't have evidence to say it's not. Okay, kind of like going back to that, guilty, not guilty thing. Okay, we don't have enough evidence to say they're innocent. We can't prove that. We're not saying they're innocent. We just don't have enough evidence to go with the not guilty. Okay, so that's what's happening here. All right, this video is getting long, so we're going to stop this one and we'll continue working on chapter 10 in the next video.